Welcome back, Precalcsters. Hope that all or most of you guys are watching this. Quick reminder, if you are watching this, feel free to go ahead and smash that like button, hit subscribe, but don't ring the bell. Remember, I post a lot of videos. Don't do it. You'll never stop getting notified. Cool. All right. So in this video, following our discussion from class the other day, I am going to work through this Chapter 2 practice or team test. Reminder, this is purely for your practice. We will not be going into great detail on these in class on Monday, but we will have time to work maybe a couple additional examples and see kind of the process for a note card. So here we go. On number 1, we are asked to write the quadratic function in standard form to identify the vertex, the axis of symmetry, and the roots of this function g of x. So as a reminder, vertex form for these guys is going to have the form y or f of x, whatever your favorite flavor is, equals x minus h squared plus k. Now, in getting to this, our first big piece is we want to make sure that this is a 1 on my leading coefficient. So it feels odd to do sometimes, but with these two pieces, I'm going to be able to make a perfect square trinomial, but I'm going to require that we have a nice 1 as a leading coefficient here. So let's go ahead and factor out a 4 from just these x terms. Now, it's going to look ugly for a second, but here it is. Now, anytime we're completing the square, we need to have a nice square at the beginning, which we do have, but we also need a square over here, which we don't have yet, and we're going to be able to obtain by adding a clever choice of 0. To do so, we're going to take, once this is in its most simplified form inside my parentheses, with a leading coefficient of 1, we're going to take this middle term, and I'm going to do the scratch work over here, which is 3/4. We're going to divide it by 2, which looks ugly, so I'm going to elect to do multiply by 1/2, which is the same thing, and we're going to square it. So a little bit of scratch work here. Let's see, that becomes 3/8, and we're going to square it. And I see that this is 9/64. So back over here then, inside of these parentheses, I'm going to add my clever choice of 0, and let's just see how that looks. We have x squared plus 3/4 x, and I am not going to change colors here, but my clever choice of 0 is going to wind up being 9/64. But I also have to subtract it since we're only actually adding 0. Plus 13. Okay, I want this piece to stay, and this piece, and this piece. This is garbage though. However, prior to being able to just remove it, we see that it's multiplied by this 4 outside of the parentheses, so we need to distribute. So I'm going to distribute this 4 only to the negative term so that we can take it out. And means it would not be distributed to the first 3, which would just stay. Here they are. I still have my plus 13 out here. And then in red, I'm going to show you just a little bit of the mental math that I would do. If I'm trying to do 4 times 9/64, which is that, and it's going to be negative, I suppose. Right away, the first thing that I notice is a 4 goes into that once, and to this 16 times. So when I actually do distribute this, it looks like it's going to be minus 9/16. Instead of writing 36/64, we just simplified the fraction. All right, on this next piece, 2 steps simultaneously going to happen. The first is, because this is a perfect square trinomial and we've done the work, I'm going to take the square root of this, the square root of this, which is square root of 9 is 3, and the square root of 64 is 8. And if I multiply these, x times 3/8, and then I double it, I get 6/8 x or 3/4, and I'm convinced. Now, if that doesn't mean a ton to you, that's all right. Because we've done everything to ensure a perfect square, we get square root is x. This sign follows us, this plus, and the square root of 9/64 is 3/8. It is squared. And I'm going to do a little bit of stuff just with mental math. If we take this 13 minus 9/16, we would need a common denominator. However, we are all permitted and allowed to use our lovely TI-84 calculators. And purely in the interest of time, I'm going to ask my calculator, what is 13 minus 9/16? It gives me a super ugly decimal that I can math frac and see that this is 199/16. Okay, we have the bulk of our work done at this point. In this form, at this point, I'm in my standard form. So I'm going to go ahead and just say, check it out. Here's g of x in my standard form. That's one part of this problem. The next part is the vertex, which once we get into this form, it's super easy to identify. The vertex from standard form is always going to be the point hk, where the only weird part about this is h is always opposite of this sign. So we have negative 3/8, I'm sorry. And it looks like the k value of 199/16 is our y coordinate for our vertex. Cool. I know that for every parabola, of which this is one because it's x squared, the axis of symmetry is the vertical line that passes through the vertex. So no additional thought there other than I need to just say x is negative 3/8. There's that value. And then finally, our last piece is our roots. So I'm going to do scratch work in a different color here just so we can split them up pretty nicely, hopefully nicely as we're going through it. So let's take a look. I need to find the roots of 4x squared plus 3x plus 13. This is my original version, and we're going to set it equal to 0. Just to highlight, you could set this equal to 0 if you would rather, and we can try that, but my mind defaults automatically to let's see if grouping works nicely. So 4 times 13 winds up giving me 52, of which I cannot find two nice numbers that multiply to be 52 and add up to 3. Okay, means grouping is out. It's not the end of the world. You have two options. You could run through the rational zero test and make a PQ list, factors of 13 over factors of 4, if you really wanted to. Alternatively, don't know that it's going to work out because I can see that there's no positive roots, and if I wanted to change signs, I would have 2 or 0 negative roots. I'm just going to commit to the quadratic formula. So I'm going to use the fact that negative b, or negative 3 in this situation, plus or minus the square root of b squared, which is 9, minus 4 times a, which is 4, times c, which is 13, all gets divided by 2a, which we have a, b, and c in this expression. So 2a just winds up being 8. Cool. So a little bit more calculator work. I know that this winds up being 9 minus, and let's see, 13 times 16. It's a larger number than I really want to deal with. Must be 208, I think. Negative, I'm just going to do 9 minus 4 times 13. And it gives me negative 199 once I simplify. All over 8. Now, I have exposure to this, but with a little bit of digging, you guys would come to the same conclusion. This is a prime number. The only thing that I can simplify out of this expression is that square root of that negative 1, which looks like I, and nothing else can be done here. I have two roots. They're both complex and imaginary. One is negative 3 plus this, and the other is negative 3 minus. So I'm going to switch back to this lovely green color, and we're just going to state the solution here. The roots, of which there are 2, are both imaginary, and they occur at negative 3 plus or minus this I root 199. Sorry about that. I root 199 all over 8. Now, heads up to the people who are traveling for wrestling or volleyball. This is a different version of the test or the practice test than I gave you guys the other day. Sorry about that. If you did the other one, I will certainly still check it and everything. But this video hopefully will be helpful. Cool. So we got the vertex, we got the axis, we got the roots, and we got standard form. I have all the points that I'm after here. All 4 points knocked out. Cool. We need to determine if this is a factor. So to do that, I'm just going to use long division because that's what's specified. I am going to use the fact that when I long divide, or synthetically, but we're going to long divide, if the remainder is 0, then the divisor was a factor of the dividend, which is kind of ugly to say, but we have it. And I'm thinking in my head 30x squared minus 3x to the first, I'm not going to write it, plus a constant. There's no powers of x missing. So here we go. I need a 30x squared. I know that 5x times 6x is going to get me there. So I'll take that 6x and I'll multiply it by my divisor. 6x times 5x is my 30x squared that I'm after. And I also get for free out of this deal minus 18x. Okay, parentheses around it to subtract. 30x squared minus 30x squared, they're gone. Negative 3x minus negative 18x changes to plus, and I see I get a 15x. And in the words of Snoop, we'll drop that like it's hot. So I now need to get rid of this 15x, and I know that if I multiply 5x by a positive 3, I'll get the same value. I get 15x minus 9. I will put parentheses to remember to subtract, and I see that I have a 17 left over. This statement right here, the fact that we have a remainder, r of x is what we'll call this, even though there's no x, is not equal to 0, implies that my divisor, which is 5x minus 3, is not a factor. Cool. And we have it taken care of. 2 points there. Awesome. So here we go. We on problem 3 are finding all real roots of this function. Now, it is not required, but just right away thinking, I'm a little bit of Descartes' rule of signs and the fundamental theorem. I know this will have 3 roots. And here's something that I noticed right off the bat. This is a positive 2x cubed to a positive 11. They don't change. 11 to negative 21 does change, and then negative to negative doesn't. Why I'm looking at this is without even bothering about the r negative part. Descartes' rule of signs tells me that I know there's going to be one real root, which theoretically we should be able to find just by using our possible rational roots from our rational zero theorem. So here we go, possible rational roots. Now, this list is going to be large, but remember, this is going to be plus or minus p over q, where p are factors of 90 and q are factors of 2. So the factors of 2 in the denominator are super easy. It's 1 and 2. And then I'm going to start thinking my way up the factors of 90. And I likely won't list them all, but I'll try. I won't even try. We'll stop, and then if I have to get more, I will. 1 goes into 90. 1 times 90. 2 times 45. 3 times 30. 4 does not go into 90. 5 goes in 18 times. 6 should go in. Goes in 15 times. And I'm going to pause there because my hope is that I'll find a number in this first set of fractions that winds up working. Now, I don't expect you guys to do, 10 different synthetic divisions when we have the technological capability to help this out. So using your calculator or just with mental math, I check 1 first. If I plug in a 1, this turns into 2 plus 11 minus 21 minus 90, which is not equal to 0, which means for 1 is not a 0, sorry. Okay, I'll then try 2, and I'll try to think this out. And let's see, 2 cubed is 8 times 2 is 16, plus that'd be a 4 when I plug it in for x, times 11 is 44, minus 42 minus 90. Also not equal to 0, which means 2 is out. Now, this could be done on your calculator again, but let's try 3 real quickly. 3 cubed is 27 times 2 is 54, plus 99, minus 21 times 3 is 63, minus 90. So what I notice is these two together are negative 153. Coincidentally, these two together are positive 153. So I just did it with mental math. You could do it with your calculator. We just found that x equals 3 is a root, or x minus 3 is a factor. So let's verify that and see if we can't get a smaller, easier factor to deal with. So I'm going to use synthetic substitution or synthetic division. And again, as I'm writing these coefficients, I am double checking in my head to ensure that none of these powers of x are missing. I go x to the 3, to the 2, to the 1, to the 0. We are good. I'm going to run through the synthetic division, hopefully fairly quick, just to see if it checks out. We get a 17. I get 51, which is negative 30. And, sorry, I don't know why I did that one. It's going to go to 0 because I'm going to write a 90 right here. And we get it. Okay, so just a conceptual kind of setup here. This thing tells me something very important. Because I got 0, I now know that my function f of x, which started as this ugly thing, has two factors. The first is our x minus 3, which is just a different way to word that x equals 3 is our root. And the other factor, if I started with x cubed, I've kicked down because I'm just dividing by x minus 3. I'm going to start with x squared. So I have 2 as my coefficient, x squared, plus 17x minus 30. And here it is. Now, as I look at this one, this piece, x minus 3, is just going to stay. I'm going to do some scratch work off on this side now, just so it can look nice as I'm doing my solution here. I'm trying to factor, to the best of my ability, 2x squared plus 17x minus 30. So I need factors of negative 60 that are going to wind up adding up to 17. And I'll erase them here in a second, but because they have to add up to a positive but multiply to be a negative, one of them must be a negative, but it must be the smaller number. So I'm already thinking negative 1 and 60 doesn't work. Negative 2 and 30 doesn't work. Negative 3 and 20 does work. These multiply to be negative 60, which is what I need, and they add up to a 17. So I'm going to replace this 17x with these numbers as a combination of x, meaning this is going to become a 4-nomial, 2x squared minus 3x plus 20x minus 30. Again, notice this piece simply replaced this. Equivalent expression, it's just written a little bit differently. Now, the reason we do this is because we can group this. I see an x comes out of here, leaves behind a 2x minus 3. And if I factor out, it looks like a 10 out of this one. I hope I don't have a mistake. We'll see. Leaves behind, oh no, I can't factor out. Yeah, I can. It's 2x minus 3. And these match, which is what I need. So I now can tell that this factored form turns into x minus 3. And we get one factor as x plus 10, the numbers that we've pulled out in front. And the other factor is 2x minus 3. And I'm just going to verify because this feels something off about it, but I'm going to double check. 2x squared minus 3x plus 20x minus 30. I'm good with this. Now, once I have all my factors, the zero product property tells me if I set each factor equal to 0, I can find these roots. And I see that this first factor, if I set just this equal to 0, I'll add 3 and I'll get a positive 3. This one, I will subtract 10 and get a negative 10. This one's a little bit more complicated. I need to add 3 and I need to divide by 2, but that's okay. It's 3 halves. And notice 10 does go into 90, so it would have shown up here. And 1 does go in, so I'm convinced. Cool. Looking at these, we have all 3 roots. We are golden. Done. Here is our solution. All right, sorry if there was an awkward transition there. I had to pause and get a drink. Let's check this out. Okay, this problem is a little bit tricky because when you do this distribution, you wind up getting x to the 4th. Now, it's positive 1, so I know it's a positive, and x to the 4th is even. 2 ways that we can write this. Even exponent, or power, degree, and positive leading coefficient. I'm okay if in class, and as we're doing these for like time purposes, this suffices. Up to the left, up to the right. Now, going further, remember that we could write this more formally and say as x approaches, doesn't matter if it goes really far to the right, so positive, or really far to the left, negative, infinity, my function f of x also gets really big, or more formally stated, approaches infinity. These two answers are the same. I'm cool with either. I prefer the second, but I understand the first. Okay, we are asked to find the real zeros of f, given that this is a factor. Now, right off the bat, from the way that this is given, we already know one factor. X is a standalone factor. Can't simplify it, there's just no constant. So I'm going to use synthetic division because I know this is a smaller factor of the whole thing. I have a sneaking suspicion that x minus 1 is a factor of this. And I'm going to confirm that using synthetic division, where I put x minus k, or 1 is the number here in this situation, and we'll run through with our coefficients, again paying careful attention to make sure I'm not missing any powers. And let's just verify that this is indeed a factor. So I get a 1, a 1, a 1, a 2, a negative 3, and a negative 3. Cool. Just like I did on the previous problem. At this point in time, we know that we have a basic factorization. At this point, it's x times x minus 1 times 1x squared plus 1x minus 3. Now, because I'm looking for the real zeros, of which there could be 4, I'm going to try my best with a leading coefficient of 1 on this term to use a shortcut. So I need factors of negative 3 that are going to add up to a positive 1. And let's see, as I'm going through here, factors of negative 3 that add up to a positive 1. It's not 1 and 3, and it's not negative 1 and negative 3. So let's take a look. And it turns out I know why this is weird and why I'm struggling with it. 1 plus 1 is 2. I even wrote a 2 here when I multiplied it. I just wrote a 1. If you didn't catch it, I changed this on my synthetic division list to a 2 because it was a 2. And I'm going to change this, which means much easier to do. 3 and negative 1 are the two numbers that multiply to be negative 3, but add up. So we'll go one more little factorization step. We get an x and an x minus 1, and then via our shortcut, I get an x and a positive 3, or plus 3, and a negative 1, or an x minus 1. This tells me that my roots, all 4 of them, which the fundamental theorem tells me we will find, they happen to all be real, not guaranteed, but they did. Let's see, we get x equals 0, we get x equals 1, and we get x equals negative 3. Now, notice I've written 1 twice only to really stress this idea. I'm going to use multiplicity when we graph this. So this is a touch and turn situation because it's a number of times it shows up as even, and then I see that we have a crossing the axis at these points when x equals 0 and x equals 3. So last little part, because we're only sketching, I'm going to use a number line to take care of this. So here we go. I'm going to throw only the places where this function can change signs, these, on my number line, and I'm going to put them in order. I get negative 3, I get 0, and I get 1. Now, if we were graphing like really precisely, we would get more information than I'm about to. But check it out. I only need one little value in here. So in my mind, I think that negative 1 is easy to plug in. And then what I'll do is if I choose negative 1 here, I'm just going to plug it in here. This would be, and this is scratch work for this, this would be a negative 1 times a negative 2 times a positive 2 times a negative 2. So let's see, negative times a negative would give me a positive times a positive 2 times a negative. This is negative. Now, turns out that it's actually the point negative 1, negative 8. If you want a little bit more detail in your graph, you can. But realistically, all I care about is the fact that it is negative. So I will use my multiplicity. I know that at 0, it crosses. So it was negative. If it crosses over, now it must be positive. And at 1, it touches and turns. So if it was positive and it comes down and touches the axis, turns around, it's still positive. And last little piece, with multiplicity, -3 was a root that showed up 1 time. So I know if it was negative and it crossed, it's now positive. Okay. For this graph, I'm terribly sorry, but I do not have on this particular program the capability to make nice straight lines, so I will try my best. If we're just doing a really rough sketch, here it is. I know that I need to go at least to -3 or -4 rather, and down to -8 based on that number. But maybe I won't even do a crazy amount of effort on the Y scale because we're just sketching for general trends and shape. So let's see, I need a -3, which I'll do -1, -2, -3, -4. There's my root at -3. I will do a root at 0, and I will do a root at 1. And I should make that a little bit more direct, or a little more to scale. So we'll say 1, 2, 3. If it's not indicated, I will always assume that a single dash represents a change of 1. So let's see, I had a root at 1 as well, and I know that I was positive on this side, so it touched and turned. It must go up like this. This is this positive section. And then it's positive still after touching this between 1 and 0. So it must come up somewhat and then touch again. And then it moves to the negative region, and it moves pretty far negative, seemingly, until -3. So it moves pretty far down until -3, at which point it's going to come back upward. Now, not a perfect graph, and in fact, I kind of hate it. I'm going to fix that section in the middle just because it's going to bug me. But these graphs, remember, aren't perfect. These are sketches. I just want to make sure it doesn't look like there was another turn happening. We have end behavior up and up, or to infinity from either direction. Everything that we had done in the previous problem applies right here. Cool. Okay, moving on. Evaluate these. When we divide with complex or imaginary numbers, our goal is to get rid of the imaginary part in the denominator. This can always happen by multiplying by the complex conjugate. Now, the nice part about this, and we'll just look at it, is the denominator has a shortcut. But let's see, I'll do the numerator first. 6 times 4 is 24. 6 times I is 6i. 4 times I is 4i. And then this last little piece is going to be plus I squared. And then in the denominator, I want you to check, but I know that if you multiply a complex number by its conjugate, it's just going to be the sum of the squares of the coefficients, which is super ugly to say, but 4 squared is 16, plus the coefficient on the I term is 1, so I'm just going to say 1. You can FOIL, distribute, make sure that checks out the same. I'm going to take 2 little steps here. The numerator becomes 24 plus 10i, plus this I squared, remember, is a -1. And that's all over 17 at this point. And what I recognize is this 24 and -1 are like terms. But because we're in standard form, I'm going to do one additional thing. I'm going to split it up to be the real part, which is 23 over 17, plus the imaginary part, which is 10 over 17. And then it is entirely up to you whether you want to put the I out here like this or attach it to the 10 in the numerator. They're both the same. Stylistically, I prefer it in the numerator, but I've written it this way because I imagine that's how you're going to do it. Cool. We have a complex number in standard form. Awesome. This one, just a little bit of FOIL. 1 times 5 equals 5. 1 times -2i is -2i. 6i times 5 is plus 30i. And then 6i times -2i is minus 12i squared. So, same 2 little steps. These I terms in the middle are like terms. Looks like it's going to be plus 28i. And then minus, and I'm going to think this out, this is 12 times -1, which winds up being minus a -12, meaning that these are going to wind up adding the opposite. And all of a sudden, we're there. 5 plus 12 is 17 as my real part, plus 28i as my imaginary part, and I now have a complex number in standard form. Cool. Couple more little problems, and we're done. Sweet. Okay, we are asked to solve this inequality. Now, remember, our function, our inequalities have key numbers, and they come in two different flavors for these types of problems. They come as roots, and they come as asymptotes. So right off the bat, I see that there's a vertical asymptote when x equals 0. If x is 0, it makes me divide by 0. Can't do it. The roots take a little bit more work. I'm going to do some scratch just down here. I know that I'm looking for factors of 20 that add up to a negative 9. I think that that means for me that I can do x minus 5 and x minus 4, because negative 5 and negative 4 are those magic numbers, which means I have roots that happen to live at x equals positive 4 and positive 5. Positive 5 if you set this equal to 0, positive 4 if we set this equal to 0. We get three key numbers that we're after. Last little piece in solving this. When I say less than 0, two things come to my mind. Less than indicates that this is going to be an open circle. We're not going to be able to touch it. And less than 0 means negative. So I'm looking at points on my number line that are negative, and I'm going to connect any of them with open circles for all of them. So here we go. Here's a beautiful number line. I'm going to put these key numbers in order, which looks like 0, 4, and 5. And I'm just going to make a note underneath each of these. These roots of multiplicity 1 tell me my function crosses. And then 0, because it's an asymptote, we actually have to check. So I'm going to plug in a 1, for example, and I'll do the same thing I did before. I'm going to plug in a 1. This is a number that I'm checking because it's in this interval. If I plug this into the original function, I'm going to get 1 minus 9 plus 20, which winds up being a positive number, divided by 1, which is also a positive. I know it's positive. And I'm going to move that just a little bit lower here. Positive. Now, because of multiplicity, guarantee that these are going to be positive and negative. So we'll check one more, and I'm going to pick something obnoxious to make it easier on myself. Let's do negative 10. Now, I would typically look at this function instead of being this form. I would think of it in the factored numerator and keep the denominator over x. This is an equivalent version. These are the same problem. I have just changed the form that they're in. So when I plug in a negative 10 into this, and I'll put it in parentheses so I'm consistent, notice what happens. I get a negative and a negative over a negative. So we get a positive in the numerator over a negative in the denominator. It says, look at that, it's negative. So if we're actually doing our graph, we're here. I'm looking for where it was negative. So I have this first piece. Everything to the left here. Nothing between 0 and 4. And then everything between 4 and 5, just not including, 4 and 5 themselves. So here's our graph. That was one of the parts we were asked. The intervals for our solution. We have two of them. We have negative infinity, working all the way to the left until we get to 0, which we don't touch and we'll indicate by a bracket. And then we will tie this together or union this with that second interval from 4 to 5, once again using parentheses because I don't touch them. Those are the open circle variations. Alternatively, though, we can also do this function, or write our solution, in set builder notation. All these values are the set of all x, such that two things must be true. This first leftmost piece says, hey, just make sure you pick an x that's less than 0. Cool, got it. Or, because we have to take a jump, we need to pick an x that's between 4 and 5, but not equal to either. So x better be greater than 4, while simultaneously being less than 5. And we now have our lovely set builder, our interval, and our graph of our inequality. Cool. So last one on this video, and we're looking at 34 minutes right now. I'm going to simplify it. Now, all these problems, what's really nice is they've been shortcut problems. So I'm trying at least to think of factors of positive 4 that are going to add up to negative 5. And because it's a shortcut, I'm going to be able to factor this like right off the bat. So factors of 4 that add up to negative 5, I think are negative 4 and negative 1. So here we go, x minus 4 over times, x minus 1 divided by, and in my denominator, there's no GCF. It's a binomial, it's a difference, and I know the square root of both of these. So I see a difference of squares where I'm just going to take the square root of the first minus the square root of the second times the square root of the first plus the square root of the second. In doing so, what I notice is that I have a common factor in the numerator and denominator that will divide out. And I'm going to do two things. First, our true simplified form of f of x is x minus 4 divided by x plus 1. But because something divided out, I'm going to indicate on part D that there was a hole at the root related to this factor. So if x minus 1 was the factor that divided out, if we set it equal to 0, I would see that there should be a graph or a hole in my graph at x equals 1. Cool. X-intercepts on part C for this problem, and I'm just going to C purely arbitrarily. X-intercepts of a rational function, remember, occur when the numerator is 0. Easy to do here. The x-intercept is going to happen when x minus 4 is equal to 0, which if we solve it, we get x equals 4. The y-intercept for a function occurs whenever x is 0. So I'll do a little scratch work over here. F of 0 winds up giving me 0 minus 4 divided by 0 plus 1, which looks like the y-intercept should happen at negative 4. We have x-intercept, we have y-intercept. Cool. We're cooking still. The domain. This is kind of a just thrown in the dark question, but any x that breaks our function. And at this point in time, only two things recall that break our functions to graph. We cannot have a square root of a negative to graph within our real numbers, but we also can't divide by 0. There are no radicals in here. We're looking at polynomial stuff. So that's good. Unfortunately, there is one value of x that would make me divide by 0, and we'll just say, hey, it's a set of x such that the only requirement is x is not equal to negative 1 because it would make us divide by 0. If you're feeling like creative and you'd rather write this as an interval, you can. We go negative infinity to negative 1. We don't touch it, and then we just pick right up as close to negative 1 from the other side as we can, and we have two ways of writing the exact same answer. Awesome. Okay, part D, we've already got part of it done. We have the hole knocked out on this graph. It occurs when x is here. The vertical asymptotes. Turns out this is the same question as the domain. I know that x cannot be negative 1 because that's what makes my denominator of my simplified form 0. The horizontal asymptotes. If I check the degree of the numerator, which is 1 in the simplified form, degree 1, and the denominator of degree 1, then the ratio of these leading coefficients is my horizontal asymptote. So here we go. 1 over 1 are the leading coefficients, and that's just y equals 1. Awesome. Okay, we have almost all the information that we need. I'm going to put a number line here just to help make sense of stuff, and I'm going to place just the key numbers on my number line. Now, that is a definition piece, which if you don't recall what the key numbers are, that doesn't mean anything to you. So just as a quick reminder, key numbers for us are roots and asymptotes, vertical asymptotes. Could be a hole, so maybe we should check that as well, I suppose. But let's take a look. I have negative 1, and I should check to see where my 0 was. I have negative 1 as a vertical asymptote. I'm going to include a hole at 1 as well on here. And then my root was at 4. So let's check it. If I plug in a 0 into my simplified form, which we can't see it on my screen now, but the simplified form of this was x minus 4 over x plus 1. And I'm just putting it so I can see it again. If I plug in a 0 into that function, what I see out of it is I get negative 4 over 1. So I'll say 0. I get a negative 4, or just a negative in general. Okay, if I plug in a 2, I get 2 minus 4, which is a negative, over 2 plus 1, which is a positive. I'm still negative, so I won't even wind up having any important part here. Because 4 is a root of multiplicity 1, which is an odd number, I know it's going to change to positive. And we just need one more check on this other side. So let's do something obnoxious like negative 10. And you could use negative 2 and get the same answer, but negative 10 allows me to really easily say, oh, that's a negative over a negative. Positive. Cool. Now, because we got a couple y values out of here, the scale is provided on here, but if I need to get all the way down to 4, or up to 4 at the y-intercept, which is negative 4, sorry, maybe I'll just make this a 2 and this a negative 2, and now I can see everything that I might need. So let's check this out. I know that there was a root for this function. We found it at, I'm trying to change color here. We found the root was at positive 4, so I'll go ahead and put a root at positive 4. I know that there was a y-intercept at negative 4, so that's the y-intercept. I know that there's a vertical asymptote at negative 1, and that's not negative 1 because these jump by 2, so let me change those. A vertical asymptote at negative 1, which roughly is here. And there's a horizontal asymptote at y equals positive 1, so similar situation, positive 1. I'm going to now draw the graph, and all I have to do is just make sure I use the information. I know it passes through this point, and that it gets really close to this asymptote. So I might start over here and say, check it out, we level off and get close to that asymptote. Now, my curve needs to bend down and pass through the y-intercept at negative 4, but notice there's a hole, and I'm going to go from the other side because it's going to be easier for me. There's a hole at negative 1. So whenever I get to this x value at negative 1 as I'm drawing my graph, I'm just going to try my best to make it a hole and check it out. There it is. We have this part of the function. We get really close to this asymptote and we don't touch it. So I'm going to show that that screams downward. And then over here to the left of this asymptote, I know that everything is positive. There's no more x-intercepts, which means the only option for my graph as a sketch lives somewhere up here. Cool. With explaining everything in super detail, this wound up taking me 43 minutes or so. I did not work this very last problem. This is one that I would like us to talk about and do together. But please don't hesitate if there's a part of this that you had issue with. If you leave a comment, I'll probably see it, or if you shoot me an email, I'll definitely see it. If there's any parts of this that you particularly struggled with and you would like me to have as an example in class on Monday, or if you want to come talk to me about it outside of class, that'd be preferred. But here is the entire worked through exam, done hopefully clearly in reasonable amount of time. Now, just full disclosure, I don't think that it would take, I know it wouldn't take as long if I weren't explaining everything along the way, which makes me think that for you, within 55 minutes, without having to explain everything as we go through it, hopefully will go, reasonably well. But don't hesitate, provide feedback, let me know if there's things you want me to change or further questions. In class, our next class, we will be making note cards together to try to summarize as much of this information as you personally need in a nice, single, easy to find spot for the exam coming up on Tuesday. So, hopefully we get a bunch of views. Remember, hit that like button, subscribe, and I'll see you cool cats on Monday morning. Later, Raiders.